Okay, so the first concept that we want to actually start after introducing a metric is the notion of a neighborhood. So X and D be a metric space, and P is any point in the metric space X, and let epsilon be greater than 0, a real number. The epsilon neighborhood of P is defined as follows. In other words, it is the set of all points whose distance from P is strictly less than epsilon. So let me explain it here. So neighborhood, so this is definition 3.15. So you see, you have a metric space. So this is always a metric space. Okay, and then I have given you an epsilon, a real number which is greater than 0. Then you can talk about the epsilon neighborhood of any point in the set. For example, I pick a point in my set and I want to talk about the epsilon neighborhood of that point. This is the notation we use. Okay, I recommend you think Euclidean in a Euclidean way about the neighborhood, but don't rely on your intuitions for proofs. Okay. So in other words, if I want to talk about epsilon neighborhoods of a point, I mean all points in my space whose distance to this fixed point is strictly less than epsilon. So it is like a circle inside the circle. If it is Euclidean space, if I give you a point there and I give you 1 or 5, any positive number, if I ask you what is the neighborhood of this in the plane, then you would say inside the circle centered at the point and radius the number that you gave. So that's exactly the same. So the neighborhood of P with radius, sometimes we can even call it the radius. This is the center of the neighborhood, and it's the radius of the neighborhood. It is defined to be a set. So in principle, there is no picture for it. It's an abstract set. A set consisting of what? Of all elements from the underlying set X, such that the distance from those points to this fixed point P is less than epsilon. This set is called an epsilon neighborhood of P. Is that right? That's the meaning. Okay, for example, let us go to the real numbers. For any real number P and any epsilon greater than 0, we want to describe this neighborhood with respect to the Euclidean metric. Okay, so example 3.16. So we are working with x equals to r. When I say Euclidean metric, what do I mean? Which metric I'm talking about in R? The absolute value metric, the standard metric in R. The distance function in R is just this absolute value. So, and then I want to know an epsilon positive is given and a real number P is also given. I want to describe what do I mean by this. But before describing, can you intuitively tell me what do you think it should be? Because now it is Euclidean space, you can work with pictures. Okay, so this is the set of real numbers. I have picked one element there. And I am looking for what? I am looking for all points on R whose distance to P is strictly less than epsilon. What is that?
Intervals.
So it means that I can go up to here, and I can go up to here. The length is epsilon. So this point will be P plus epsilon. This point will be P minus epsilon. Okay, so what is your guess for the question mark?
That interval.
The interval from P minus epsilon to P plus epsilon, but not including P minus epsilon and P plus epsilon. So if I want to draw the picture, this will be the picture. So the neighborhood is just this line segment without the endpoints. But if you want to write the definition, how do you write it? So this is important. Both of them are important, okay? But for proofs, this is more important. That is intuition, which help you to find a path to the proof. Okay, so what is epsilon p? This is the set of all x's where, in this case, this is r, such that what happens? The distance from x to p, but distance is defined in this way, to p is less than epsilon. Do you agree? This is the definition. But you can do this in this way. The absolute value is less than epsilon, so this means that number should be sandwiched between epsilon and minus epsilon. And then I can add p to all sides of this inequality. Let me write it here. So it becomes p minus epsilon less than x less than p plus epsilon. So if I want to follow definition, the neighborhood is this set. And that is exactly, how can I show, oh sorry, this was R. But do you remember, there is a notation for this kind of set, and that is exactly what we guessed from the picture. Is that right? So your intuitive picture is completely aligned with the abstract definition. But for the cases that are counterintuitive, this is the only way we can do, not based on intuition. Any questions? Okay. So let us go to the next one. This one is also good, a good example. It's exactly the same, but I have changed the underlying or the ambient set. So example 3.17, the difference is important to acknowledge actually here. So x is this one, but I will keep the metric the same. So I am changing the ambient or the underlying set, keeping the metric the same. And I am asking you the same question. So it means the whole universe is collapsed to this line. So there is nothing outside this line. So in principle, I have to, if I want to imagine that space starts from 0 and goes to infinity. Okay, so this is my x now. And I am picking one point in my space, and I want to find the neighborhood of this point. How do you think it will change? Intuitively, but because that's exactly, you can do it at home. Let us say that this epsilon, if the epsilon is very small and p is here, it will give you the same. Do you agree? For example, if epsilon is this much in this picture, and so you go p plus epsilon, p minus epsilon. But if epsilon is bigger, for example, let us say that epsilon is this much. Okay, so then what happens? P plus epsilon is on the safe side, but p minus epsilon will go outside of your universe. So if epsilon is this much, okay, can you tell me what is your guess about the neighborhood of this, for this epsilon?
It goes from 0.
It goes from 0. So it becomes 0 up to p plus epsilon. So it means that if you change the underlying set, the neighborhood might change. Is that right? Is that understandable? If epsilon, of course, but you have to find the correct, rigorous way of proving it. Okay? Do you agree with what I said, yes? Because if epsilon is less than this distance, yes, then p minus epsilon and p plus epsilon, it works fine. But if this epsilon is greater than this distance, then p minus epsilon will go outside. And then I should keep it from 0 to p, 0 to p plus epsilon. Okay, so let me test your understanding. This is not in the slide. If I have this one, not in the slide, okay? If I have x to be r, but d is the discrete metric, what do you think will happen for neighborhoods? D, the discrete metric. Okay, and I want you to, so P belongs to R, epsilon is positive. I want to talk about this. Can you guess what happens? So I write my definition. The definition is always rely on definitions. So x belonging to x, which is in this case R, such that the discrete metric distance between the point P and the point X is less than epsilon. Okay? It's a very good example. Can you tell me what is inside? So let me tell you something. If epsilon is a number which is greater than 1, if I give you the radius bigger than 1, what do you think will be accommodated in this set? All the points from R whose discrete metric distance from P is less than an epsilon, in which epsilon is greater than 1. Yes?
It's all of them.
All of them. Because the discrete metric is either 0 and 1. Okay? And if I give you epsilon a number greater than 1, all the numbers will fit. So this becomes what? What I should write? It becomes the R itself. Yes? And can you tell me what happens, because there are other scenarios. Epsilon is a positive number. What happens if epsilon is somewhere between 0 and 1? For example, 1/2. I want to have the distance from x to p less than 1/2. Yes?
It's just P.
P. Just p. But do you think this is a correct way of writing?
No, because if it's equal to 1.
It's a set. So you have to write it in that way.
But if it's less than or equal to 1, doesn't that mean you could also have it be all of them?
No. Even it is 1,
Okay.
because this is a strict.
Oh yeah, that
Then
one.
exactly that one. Okay? So that's a very good example. It's a counterintuitive example. So it means that if I give you epsilon to be 5, it means all the points from in R has distance are within the interval, within the neighborhood, with radius 5. This is a very good example. I don't know why I missed them here. Any questions? Okay, so let us now go to the next one. And this one is very interesting. I want you to think about this yourself. So it means that usually when we go to 2 dimensions, what is your guess about the picture in Euclidean space about neighborhoods? Circles. Yes? Because I want to, if I am in 2 dimensions, and if I give you a point here in 2 dimensions in Euclidean space, if this is a point, and I give you epsilon, for example, to be 1, and I ask you to find all points on the plane whose distance from P is less than 1, it will be every point inside the circle centered at P with radius 1. Okay? But if you choose different metrics, you will have different shapes. And these metrics that I have defined here for you, do you remember we had about D2 and D1 and D infinity? So I really want you to check at home that these are the pictures you will get. So this is the intuitive one. These two are different ones. This one is if I choose D1, the maximum metric. What was the name? The taxi cab metric. And this one if it is the maximum metric. Okay. Any questions? But you should sit down and really do it so that you can digest these concepts. Okay, the next one is a very important notion of an interior point. So, because there are a lot of definitions, so what is your intuition if you are a mathematician and you want to define an interior point of a set? Because every one of us has some kind of intuition about, for example, if I give you an interval, so do you think 0 is an interior point? So interior means in the flesh of the set, within in the meat of the set, inside it. Okay. So 0, do you think is an interior point?
Yes.
Yes.
Could include that, right?
It seems no. If of course it depends on the ambient space. I am talking about the ambient space R. So 0 is not a good choice for an interior point. It is good for a which name? A boundary point or an end point.
Sure.
Yes. But what about 1/2? What is your expectation? 1/2 is an interior point. Yes. So if you want to generalize this idea into an abstract metric space, how do you define an interior point? So you have a set. Okay. You say that a point is interior if what happens? By the notion of neighborhood. If you can find a neighborhood inside the set containing P, and that's exactly the definition. Yes? So we say that E be a subset of this. Let me explain it on the board, that would be easier. So if X and D is a metric space, and then I have E a subset of X, and then a point P is in X. Is in E. Be careful. A point P is in E. We say that P is an interior point of my set. This is a picture in Euclidean space. It will always guide me to remember things, to understand how to do, but I cannot rely on them when I want to do the proof. Okay? So when I say that P is in the flesh of my set, it means what? It means that I can find a neighborhood around that point which is still guaranteed to be completely in my set. Okay? If, of course, I am not saying that this radius is fixed, because if this P is very close to the border, I have to choose that epsilon very smaller. Okay? But if it is in the middle, I can have the possibility to have it bigger. So I would say that P in E, P is an interior point. If what happens, can you finish it? If I want to say epsilon greater than 0, I want you to fill up this gap with a quantifier for all or exists. Okay? Such that n epsilon of P is a subset of E. So I want you to fill this gap with this symbol or this symbol. P is an interior point if, just say it.
If there exists.
There exists. Okay, so this I have to put there exists an epsilon greater than 0. If I can find, no matter how a small epsilon is, if I can find one so that this circle is really inside the flesh of the set, then that is an interior point. Is that right? So, and then if I for example, in this picture, is this an interior point? No, because if you see, if I draw a circle, no matter how small I make the circle, this cannot fit into the flesh of the set. So that point is not an interior point. Is that right? But other points are interior points, and this dot means that these are not included in the set. Okay, so that is the meaning of an interior point. And now the collection of all interior points is called the interior of the set. And it is denoted in your book by this for interior, but I am lazy to write it. That's more suitable. I will show it with this symbol. Okay, so it means that all the points that are interior points is the interior of the set. For example, can you tell me, if I want to show you the interior points, what should I do in this picture? I have to make them dotted line. Because these points are the only ones that are in the set, but they are not interior. If I take those boundary points out, what is left is the interior of the set. Is that right? So that is called interior. So, for example, do you think one of them should be true or none of them is true? Or what is your opinion about this? Is one of them definitely true? First one. Number 1. Yes? So always remember, the interior is always a subset of E. not necessarily equal. So this one might be true or might be false, but this one is always true. And it's clear because I am telling you P within E is called an interior if it has extra property. So every interior point should automatically be inside the set itself. Okay, any questions? Okay, so this example is a good one, but I will not do all the parts of it, but let us do some part of it, okay? So based on your intuition, I don't want to write it on the board. Can you see part one? Part one, the ambient space, the underlying set is just a normal real number, the set of real numbers, and I have given you that interval, which includes 0, excludes 1. And D is the Euclidean metric. I want you to find the interior of this set. What is your intuition about the interior set? So let me write it here. So X is R, and E is what? 1. So what do you think? This is 320. So if I ask you what is the interior, because this is completely, when I talk about R and I talk about Euclidean metric in part 1, this is Euclidean metric. What is Euclidean metric? The absolute value metric. Okay? So what do you think will be the interior of this? Yes?
It's the, I don't know what it's called in English, but it's like the region with normal brackets. So it's...
Yes. Yes, that's the interior.
What's the name of that?
Yeah, we call it brackets.
Yeah, no.
This one is called square brackets.
Yes, but
open interval.
Open interval.
Yes, and then we will see why it is called open, because later we will talk about open and closed sets in any metric space. So this is interior, okay? I am just doing it in a lazy way, so I'm based on intuition. But intuition is not always good, because now. So let me ask you another question. So when you wrote this to me, it means that you realize that 0 is not an interior point. And is that understandable? Because if my ambient space is the R, and I start from 0 up to 1, so let me write it like this. 0 is filled, 1 is excluded. Okay? So 0 is not an interior point. Why? Because no matter, do you remember what are the neighborhoods on R? Euclidean space neighborhoods are just open intervals. So if I want to have an open interval around 0, no matter how I make this small, I will not be within the set. So that is why 0 is excluded here. But now my question is that, let me change the ambient space. So let me change it to, what was that number 2? Yes, 0 and 1. Okay, and then I give you E. I keep the same metric, the same Euclidean metric, but I have changed my set. And if I ask you what is E interior?
It's E now.
It's E. So it will be this one. Yes? So can you see why 0 is an interior point? So can you tell me what is your neighborhood then?
It's just, it doesn't matter, technically, right? Because we said...
No, it matters, because you cannot also go beyond your set. So let us say that, okay, my claim is that n with radius 1/2 at 0 is a subset of E. If I can show you this, then I am done. Because if I want to show that 0 is an interior point, I have to present a neighborhood of that point which is completely inside my set, is contained in my set. But let me ask you to calculate this one. How do you calculate this? You would say all x's coming from the ambient space such that the Euclidean distance, because here the metric is Euclidean, the distance from x to 0 is less than 1/2. But this is Euclidean metric, so it becomes absolute value of x minus 0 less than 1/2, which means all numbers here which is between minus a half and a half. So let me write it for you. So this becomes x in 0 and 1, so that minus a half is less than x less than 1 half. But what is the final answer to this? Tell me all x's within this set which are between minus 1 half and half. What is that?
0 to half.
0 to 1 half. Yes? So now, do you agree that 0 to 1 half, including, excluding, is a subset of this set? Yes. So I was able to find the neighborhood which is completely in my set. So remember, these ideas, Euclidean one is the most natural one, the most intuitive one. But in metric spaces, you might have counterintuitive scenarios. Is that clear? Okay. So it means that in all these topics, to both the underlying set matters and metric matters. Both of them matter. If you change one of them or both of them, the answers might be different, even if you have the same set involved. Is that right? Okay. Now let us go to the next one. So I want to wait a little bit for you. Consider Euclidean metric space R and let Q be the set of rational numbers and I the set of irrational numbers. What is your guess about the interior of Q and interior of I? So X is R, and then D Euclidean metric. Again, when I say Euclidean metric on R, means absolute value x minus 1. Okay? And then I am asking you about the interior of Q. So you should have some kind of intuition about your answer and then prove your answer. So you should have some kind of an educated guess.
Is it a Q, maybe?
Just everyone think. Because if you can manage that, it means you understood more or less everything. It's a very simple example, but you have to think abstractly. Let me repeat something. Are you thinking about all possible numbers or a fraction of numbers? Which part you are looking for to find the interior of Q? This is important. When you want to look into the interior, you shouldn't go beyond the set itself. You remember, I asked you which one is correct. The interior always is a subset of the set itself. So, for example, if you want to look at the interior of Q, look inside the numbers, the rational numbers. Do you understand that? If you have an irrational number, just ignore it, because irrational number is not within your set. Interior points should be within your set, but not necessarily all of them. For example, these points are on my set, but they are not interior points. Okay? So now can you tell me what is the interior of the set of rational numbers? How you should think? You need to think about rational numbers. Pick one rational number in your head. 1/2. Okay? Can you find a neighborhood of 1/2, which is where? Completely where?
In Q.
In Q. Is that right? But you are working in a Euclidean space. So then what is the neighborhood of Q? So I would say that, okay, what is your guess?
It's just Q, no?
No. Empty. Nothing there. Yes? Because let me say, claim Q interior is empty. If you don't believe, then we'll say let Q be the interior. Okay? So Q interior should be a subset of Q by definition. So then Q is also a rational number. Yes? So if I talk about the interior point, I have to talk about a rational number, because irrational numbers are not within my set, so they cannot be even an interior. They cannot be an interior. But can this be an interior point? If yes, it means that there should be an epsilon greater than 0 such that that neighborhood, okay, becomes what? A subset of Q. Do you agree? This is the scratch paper work. If Q is supposed to be this in this one, so if you believe in this, you have to believe in that. That's the meaning of interior point. But can this happen? No, because we learned about this. In Euclidean space, can you tell me what is this one in Euclidean space? It is just Q minus epsilon and Q plus epsilon. Okay? So do you believe that this is totally in Q? No, because it doesn't matter. You see, Q is a rational number, and I am choosing an epsilon. So Q plus epsilon will be here, and Q minus epsilon will be here, and the neighborhood is from here to here. Do you think that this line totally lies in Q? No, because it contains a lot of irrational numbers within it. So it doesn't matter so you might say that let us make epsilon smaller, but it doesn't matter. If I make it smaller, it will still include a lot of irrational numbers, infinitely many irrational numbers. So there is no rational number in the interior of Q. So it means the interior of Q is empty. Yes? So interior of Q is empty. Is that right? Yes or no? Okay. But let me ask you one nice question. Let me change the metric to discrete metric. So how it will affect the interior of that Q? Is it on the board? Yes, it is still on the board here. Do you understand the question? The same set, the same underlying set, I changed the Euclidean metric to discrete metric. And I am asking you the same question. Very beautiful subject, you know. You have to learn to think counterintuitively. No answers?
It's Q, right? Or I mean, it depends.
It's
on
Q.
epsilon.
No, it's Q itself.
Yeah.
Suddenly it becomes Q itself. Do you agree? Because let us say that D is discrete metric. Okay? So, and I will choose epsilon to be 1/2. And Q is a rational number. According to what we did here, if epsilon is between 0 and 1/2, this neighborhood only contains Q. What was Q? Q was a rational number I chose. Do you agree this is a subset of Q now? Yes. So I have my neighborhood within the flesh of the set. Because my neighborhood only contains one point. And that's the center. Okay? So you see, this is very counterintuitive. So this is usually the one we are comfortable with when we are working with Euclidean spaces. If I change the metric, suddenly the interior becomes Q. Every point is an interior. Understandable? Yes or no? Yes? But at least you understand what is going on. If you go and sit down and think about it yourself, you probably understand what's going on. Okay. So now the notion of open set. So the notion of open set and closed sets are extremely important in this topic. So a closed or open set. You already know about the open interval and closed interval. These are generalizations of those concepts to any metric space. Okay, so let me define it for you here. Let X and D be a metric space. A subset of the metric space O for open is called open if every point of O is an interior point. Very simple. Is that right? And then I want you to tell me how should I write the mathematics. But for example, is this set an open set?
No.
No, because there are some points that are not interior. There are some points in my set that they are not interior, so this is not open. Okay? If I want to make it open, what should I do? intuitively. I will take this one and put dot, dot, dot there. It becomes an open set. Okay? So open means it hasn't any border around it. It's open. You can move out from the set. That's why it's called open. And you already know what closed mean later. So closed means there is a fence around it. It's closed. You cannot go out. Well, these are the reasons we call them open and closed. But now, what I want you to tell me, define open in a mathematical language. Okay? So of course, because there are many definitions, you cannot memorize all of them. So you should be able to visualize it in Euclidean space and then abstract it out. So can you tell me, when I say that X and D is a metric space and I say O is a subset of X, I call O open when what happens? O is open if and only if what happens? Every point is an interior point. What does it mean? It means for every point you choose in your set, this point is an interior point. It means there exists an epsilon greater than 0 such that a neighborhood of that contains in your set, is contained in your set. Okay, so don't memorize them because it is not possible to memorize all these quantifiers and things like that. It's better to visualize. Any questions? Okay, and is the one below clear for you? This is a better definition, simpler way of defining. We can say that O, do you remember, O interior is always a subset. This is the question I asked you and you answered correctly. So this is always guaranteed. If it is open or not, it doesn't matter. This is always true. But if the set is open, can I write it the other way around? If the set is open. Yes, because the set is open if every point of it is an interior point. So then if you compare them, it means that O is equal to O interior. So this is a very good way. I can say that a set is open if and only if it is equal to its own interior. These are very simple concepts, but you have to sit down and think about it. Any questions? Okay, so I have written it for you. Oh, okay, now you understand that. For example, why this interval was called open. Do you remember from very early times, this interval was called open for you? Do you know why? Because now every point of your set is an interior point. That's an open one. Okay? Okay, so this is the open interval. Okay, but be careful. What about this set? Is it open? No, why?
Because B is not
B is not interior. So these are very simple concepts. Okay, so let us see how many slides are left from this one. Okay. I want to see if I want to prove this one or not. Okay, so that's a good idea. Let us prove this one, because this is one of the very simple theorems that is possible to prove very simply. So what is the idea? Do you remember we talked about neighborhoods before? Neighborhoods are subsets of my metric space. And now we learn something about being open and not open. The claim is that if you have a neighborhood, the neighborhood is an open set. Yes? Is that understandable? Okay, but again, I want to rigorously prove it for you because this is a very simple theorem at this level, but it captures the essence of these kind of techniques. Okay, so how should I prove this? 3.25. I have a neighborhood, so I would say that X and D a metric space, and I have a neighborhood. Epsilon is a positive number. The claim is, and let us choose P in X, the claim is N epsilon P is open. That's my claim. Okay, but I cannot rely on my intuition. I have to do it rigorously, but I can use Euclidean space to get a feeling how should I continue. Okay? So, what do I have in my hand? I have a neighborhood. Neighborhood in Euclidean space is a circle without the rim. Okay, so imagine it is not. My argument will not rely on my shape, but it will help me to understand how to proceed. So imagine that you have, this is your neighborhood. Okay, and I am anticipating this is going to be an open, so I put dot 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 around it. Okay, it's not very clear yet. So when I say that I have a neighborhood, it means I have a center. This is a scratch paper work. Okay, and then I have a radius, which in this case I called it epsilon. Now I want to show you this set is open. I have to respect the definition of being open. So tell me, what is the first thing I do? This is the proof now. I want to help you to understand what to do, because this is also simple. If you get the intuition, like algebra, you will probably do a lot of things yourself. Okay, so the first thing I want to do, I would say let what? I want to show that the set is open. What should I do? I have to show that every point within the set is an interior point. So what do you think I would say? I would say let, for example, Q be inside this. Yes, we show that Q belongs to where? If I can manage to do this for you, you're done. Because Q is an arbitrary point, and I am showing that any arbitrary point is an interior point. So, but then again, you go to a scratch paper, because we don't know what to do now. We go to scratch paper, try to visualize it. So let me just put this point Q. Okay? I want to convince you this Q is interior. What should I do? I have to make sure that there is a neighborhood around it, which is completely within my set, but my set is another neighborhood. Is that right? Yes? Okay, now the only thing that I have to present is the radius of this new neighborhood, so that it is somehow guaranteed that this orange one is still within my set completely. So this means that I should have an educated guess for the radius of this new neighborhood, so that I am convinced it will not go beyond my original neighborhood. Can you come up with that yourself? Because the argument should not rely on a particular picture. This picture is good to know what to do, but then you have to go back and write the rigorous proof. So can you guess, for example, can I make this one this big? No, there are some limitations. So I have to find out that limitation. So for the time being, I'm looking for this radius. So let me call the radius delta. Okay, so I want to find a threshold for that delta. It is very clear that if I choose Q and closer to the center, this delta can be bigger. But if I am choosing it very close to the rim, this delta should be smaller. So delta somehow depends on the distance of the point that I have chosen to the center of the original neighborhood. Okay, so what do you think I will do here? So let us connect these 2 points because I want to get an intuition. Yes. So if this delta is here, I cannot make delta bigger than that. Do you see? If delta goes beyond that, then I am in trouble. So it means that I have to keep the threshold of delta smaller than this much. But how much is this much? From here to here is epsilon. Yes? And then from here to here, be careful, P and Q are fixed. P was fixed from the beginning, Q I fixed it myself. Okay? So what is this distance? This is the distance between P and Q and P. Doesn't matter, of course, because that's a distance. Okay? Do you see that picture? Okay, but now And what can I say? What is your guess for delta? So I would say claim, and I will wait for you. Yes?
It's, I might be wrong, but strictly less than
Strictly less than?
half of epsilon.
Not half of epsilon.
It's epsilon minus d.
Epsilon minus this distance.
Oh yeah, yeah.
Yes? And I think this one also works. So claim. Claim is this. N of delta Q is a subset of N P epsilon, where delta is epsilon minus dpq. Okay? So you see, it was not easy to just come abstractly with this educated guess. Okay? So I went to a scratch paper, drew some picture in Euclidean space that I am more or less good about it. My intuition is good there. And then I detect something there and then brought it back to the world of abstract mathematics. But the proof is still left. Okay? So my claim is this. Now again, how do you think I will proceed? So remember, I wrote this is the proof, rigorous proof. I wrote this. I didn't know how to continue. I went to scratch paper. I discovered something useful, and I came back as a claim. I didn't have any claim there before going to scratch paper. Now I have a claim, and then we can start fighting, okay? And now I want to prove this. But now I want to prove this again. Don't forget what I told you in abstract algebra. That was an abstract algebra. This is analysis. How do you think I will start? I will say let yes, yeah, this, I have to bang my head to the board, you know, because this should be a milliseconds. Let what? Yes?
Delta B epsilon minus.
No, this is under the claim. Everything is in the claim, but I want to start to prove the claim. I start with some sentence. Let what? 5 seconds. 1, 2, 3, 4, 5. Yes. No, I haven't. I was not able to teach you this. What is this in mathematics?
Alltså det är proven that is alltså equivalent.
No, this one is what is called in mathematics. This is a set, and that's another set. You want to prove a set is a subset of set. There's only one way. So that's the way that you have to conditional your brain. Yes. What should I do? Let
Q be in.
not Q. Q is already used. So let
Another
X belongs to N
to the first.
delta Q. Okay. If you want to be a good teacher, we show that. Otherwise, you don't need to write this. We show that what?
X is in the other.
That X is in N P epsilon. Yes. Do you agree? This is what I want to prove. Okay. Now, this one is a matter of seconds, in principle. But then again, you go back to the world of analysis, which is new to you, so you can be a little bit slow now. 6 seconds. Okay, so what should I write now? X belongs to this neighborhood. What can I conclude? Definition of neighborhood. This is the center of the neighborhood. This is the radius of the neighborhood, and you know X is there. What does it mean? It means the distance from here to the center is less than what? The radius. Do you agree? But what did I do this scratch paper work to understand what can I choose for delta? Okay, so instead of this delta, I put my claim in. Okay, and by the way, this is important to know. Okay, there is one caveat there I want to ask you about. I was a little bit curious. Okay, but instead of delta, what can I write? Is less than what? Instead of delta, I put this. Do you agree? And then what do you think I will do now?
We compute the distances? No, we don't.
No, your goal, you know your goal. What is your goal? Your goal is to show this chosen X lives there. In order to show that X lives there, you need to prove to me that the distance of that X to the center of this neighborhood is not bigger than its radius. So I want to find I want to somehow know the distance from x to the center of this neighborhood. So what I am interested in, I am interested in the distance from x to p. Is that right? To make it less than epsilon. So epsilon is already there, less than epsilon is already very good. So what do? I move this to the other side. Okay, so then what happens? dx in q plus dp and q is less than epsilon. Yes?
But we know that the distance between x and q and plus the distance between p and q is,
This is the same because of symmetry,
yes, it's strictly less than
because of the triangular property. Yes? So this means that dx and q, x and p is less than epsilon. Do you agree with me? Because dx and p is less than this sum because of triangular property. Yes? And this is smaller than epsilon. And then, can I conclude that we are done? The distance from my point to the center of this neighborhood, p, is less than the radius of the neighborhood. So this means x belongs to the neighborhood. Yes? Sorry, except. Okay? But do you see everything works fine for you or not? But do you see what was a little bit mistake here? I mean, I hope that this is not a bad one. Okay. So you know, this is, in principle, I have to convince you about delta. Can delta be any number? Because when I talk about the radius of the neighborhood, that number should be positive. Is it guaranteed that this delta is positive?
Yes.
Because it is extremely important. That was part of the proof. I forgot. Okay, so I have to convince you that this delta is always defined. Epsilon is a number, a real number. This is also a real number. Subtraction is a real number. But if it is going to play the role of the radius, it should be also positive. Do you believe that this number is definitely positive? Why is that?
Because this, since we're talking interior points, P and Q, you can't get on the rim, right? So epsilon will always be bigger than the distance.
Yes, because where was Q chosen?
Yeah.
But abstractly, this picture is guaranteeing you this is not negative, but rigorously this comes from this fact. That what? The distance from P to Q is less than what? Epsilon. So this number is definitely positive. So I am on the safe side. Is that understandable? So these gymnastics between a scratch paper and going back and going into scratch paper, coming back is very important. But of course, there are very, very hard theorems in analysis. Intuitively, most of them are very clear. So it was already clear for you that this should be the case for a neighborhood. But this is the rigorous proof for that. And this type of a proof is a typical analysis proof in metric spaces. Okay, any questions? Okay, so I will stop here. I will take the rest of it from the notes. And then we will have 2 lessons this week. We have to finish metric spaces this week. Otherwise, we will be behind the schedule. Any questions? No? Thank you very much.